Hello and welcome. My name is Deokgeun Park and I'll be presenting today on a method of mapping heat exchanger as simple polynomials. As heat exchangers are widely used, this method can be applied in a variety of applications. However, today this mapping method will be presented in a context of heat exchanger geometry optimization and chillers.
Chillers are large and expensive systems that are widely used in building and industrial process cooling. As a manufacturer of these chillers, the key part of product development process is the rapid and comprehensive optimization of the heat exchanger geometries. Whether it be the redesigning of current products or development of new chillers, the nature of this optimization process is iterative. Let's see what happens if iterative heat exchanger models are a part of this optimization process.
Shown on the left is a flowchart showing the optimization process with iterative heat exchanger models nested inside of an iterative system model. The resulting nested iterations caused by the heat exchanger models cause a significant increase in computational time. In order to address the issue of long computational time, non-iterative heat exchanger models can be used in the optimization process. And this is how the flowchart looks like after implementation of non-iterative heat exchanger models. The computational time to solve the system optimization has decreased from the elimination of the nested iterations. Artificial neural network model is one way to replace the iterative models with non-iterative ones. ANN seeks to mimic the human brain by empirically relating the input data to the output data with layers of neurons in between them. This data-driven modeling needs input and output data and does not require a physical model. This can be convenient if one is generating a model based on data. However, the optimal number of neurons and the hidden layers is currently unknown, and due to this reason, ANN model requires an optimization of these parameters. Unlike the ANN model, finite control volume model captures the detailed physics inside of the discretized heat exchanger element and requires iterations to solve. In order to address the shortcomings of both ANN and finite control volume models, a method of mapping heat exchanger as simple polynomials will be developed. Although this method is universal, a finite control volume model of flooded shell and tube type heat exchanger is chosen in this presentation for demonstration. The resulting non-iterative heat exchanger model will later then be used in chiller optimization and comparison case study. First, the heat exchanger was discretized into elements and appropriate heat transfer correlations were applied from the literature. Then, with the finite control volume model, the heat exchanger's operational and design spaces were randomly sampled using Monte Carlo sampling method. Shown is the sampled heat exchanger effectiveness, which is defined as heat exchanger capacity over the secondary fluid and refrigerant inlet temperatures, secondary fluid specific heat, and refrigerant flow rate. Then, using linear regression, the performance of the heat exchangers were fitted as a function of design and operational variables. Heat exchanger effectiveness, mass of the refrigerant charge inside of the heat exchanger, pressure drop across the heat exchanger, and heat exchanger mass were fitted as a function of the heat exchanger design variables, secondary fluid inlet temperature, inlet refrigerant pressure, quality, and mass flow rate. Shown is the comparison between the data and the fitted points for the heat exchanger effectiveness and charge. As you can see, the prediction matches up well with the data. Heat exchanger mass can also be accurately represented with this method, as shown in the comparison. With heat exchanger mapping established, we'll use the mapped heat exchangers to conduct heat exchanger geometry optimization in chillers. Two different types of compressors will be used to compare their effects on each of these three scenarios. First scenario is the baseline case, where you are running the system as it is. Second case is where you're minimizing the refrigerant and heat exchanger material costs while meeting the 350 kilowatt capacity requirement and IPLB 8.0 efficiency requirement. Lastly, the lifecycle cost case is where the entire lifecycle cost of the product is considered in the optimization. Presented here are the assumptions made. 5 years of product lifecycle is assumed with 876 hours of yearly operation and 10% salvage cost at the end of product's life. Here are the results of the 3 case studies for each of the compressor types. All the cases were plotted in comparison to the baseline positive displacement compressor case, case 0, where the system ran as it is without any geometry optimization. Case 1, positive displacement compressor configuration, was able to meet the capacity and the IPLB requirements while decreasing both the first and the operational cost. Case 2, positive displacement compressor configuration, was optimized for its lifecycle cost while meeting the capacity requirement. The first cost increased slightly while the operational cost further decreased compared to the case 1. Cases with centrifugal compressor were boxed in light blue, and case 3 is the baseline. Baseline case capacity for a chiller with centrifugal compressor is slightly higher than the required 350 kilowatt, and the IPLB is lower than the required 8.00. Case 4 optimizes the heat exchanger geometry while meeting the capacity and the efficiency requirement. Shown on the bottom right corner, case 4 increased in first cost, while the operational cost decreased from meeting the IPLB efficiency requirement. Finally, the lifecycle cost of the chiller with centrifugal compressor was optimized using the heat exchanger geometry variables. The first cost decreased slightly, and the operational cost decreased significantly from the baseline. Using the mapped heat exchangers, these thermoeconomic comparisons between different chiller configuration was possible. From this study, it can be concluded that the use of positive displacement compressor will be more advantageous when the lifecycle cost of the chiller was optimized using the heat exchanger geometry variables. In summary, we developed the heat exchanger mapping process and used it to optimize heat exchanger geometry in chillers. In the case study, heat exchanger geometry was optimized to meet the capacity, efficiency, while minimizing material and operational costs. We were able to compare the economics of using a positive displacement compressor over the centrifugal compressor by using the simple polynomial heat exchanger mapping method. I'd like to thank my advisor, Dr. Brian Rasmussen, for his guidance. And I'll also like to thank my friends at Thermal Fluids Control Lab and my family for their help and support. The study was sponsored by Emerson. However, the opinions made in this work and presentation was that of the author only and does not reflect that of Emerson. Thank you very much. And at this time, I will take any questions.